Hello students. So this is Springs part 5. In this video, we will discuss some of the concepts related to springs. So first of all, let's discuss springs in parallel. So you can see in the diagram, there are two springs K1 and K2. K1 is the stiffness of the spring 1 and K2 is the stiffness of the spring 2, and load W is acting on the springs. So W is the load carried by the springs. W1 load shared by spring 1, W2 load shared by spring 2, K1 stiffness of spring 1, K2 stiffness of spring 2. A little consideration will show that when springs are connected in parallel, then total deflection produced by the spring is same as the deflection of the individual springs. So you can see if we press this, at this point downwards, then deflection in both the springs will be same. So we can say that total load W is divided into W1 and W2. So this W is divided into W1 and W2, and you know that load is equal to deflection into stiffness. So let's say deflection is delta and equivalent stiffness is K. So which is equal to deflection into stiffness 1 plus deflection into stiffness 2. Since deflection is same for both the springs, therefore deflection will be written as delta. So deflection will be cancelled out and we are left with K is equal to K1 plus K2. So total stiffness is equal to stiffness of first spring plus stiffness of second spring. So K is equal to combined stiffness of the springs and delta is the deflection produced. This is the case when the springs are in parallel. Now, if your springs are in series, then what will happen? So let's say this is your fixed point, this is your second spring, and this is your first spring. And at this point, load is acting W. So K1 and K2 are the stiffness of the springs. So W is equal to load carried by the springs, delta 1 deflection of the spring 1, delta 2 deflection of spring 2, K1 stiffness of spring 1 and K2 stiffness of the spring 2. Stiffness can be written as load upon deflection. So a little consideration will show that when springs are connected in series, then total deflection produced by the springs is equal to sum of the deflections of individual springs. Means the total deflection, for example 5 centimeter, will be equal to deflection in spring 1, for example 3, and deflection in spring 2, for example 2. So total deflection 5 will be 3 plus 2. So total deflection of the spring, that is delta, is equal to delta 1 plus delta 2, and deflection can be written as load upon stiffness. So we have written W upon K1 plus W upon K2. W will be cancelled and we are left with 1 by K, that is combined stiffness of the spring is equal to 1 by K1 plus 1 by K2. So this is the relation which is used for springs in series, and this is the relation which is used for springs in parallel. Now let us discuss the case of concentric springs, or we can call composite springs. So concentric springs are two springs which are having the same center. So you can see in the diagram, this red shade one is the outer spring, blue shade one is the inner spring. Inner spring have diameter D2, coil diameter. Outer spring has diameter D1, and there is a clearance between the two springs. It is written as C. Wire diameter of the inner spring is D2, wire diameter of the outer spring is D1. In first case, the length of the both the springs is same, but in the second figure you can see the length of the inner spring is L2 and length of the outer spring is L1. The diameter of the outer spring is D1, diameter of the inner spring is D2, wire diameter for the outer spring is D1, wire diameter for the inner spring is D2, and C is the clearance between two springs. So a concentric or composite spring is used for one of the following purpose: to obtain greater spring force within the given space. So by using two springs instead of one, we can have greater spring force. to ensure the operation of a mechanism in the event of failure of one of the springs. So if, for example, you are operating a mechanism and your one of the spring fails, in that case, the your mechanism will continue to work because you are using two springs instead of one. The adjacent coils of the concentric spring are wound in opposite directions to eliminate any tendency to bind. So as you can see, the winding of the both the spring is in opposite direction. As you can see in this diagram, this angle is upward, this angle is downward. So the winding of the both spring is done in opposite direction to avoid any binding of the two springs. So let W2 is the load shared by the inner spring, W1 is the load shared by the outer spring, and W is the total axial load. D1 is the wire diameter of outer spring, D2 is the wire diameter of inner spring, D1 mean diameter of outer spring, D2 mean diameter of inner spring, delta 1 deflection of the outer spring, delta 2 deflection of the inner spring, N1 number of turns of the outer spring, N2 number of turns of the inner spring. These notations are same, just we will use suffix 1 and 2 for the outer and inner spring respectively. This is the relation you have to remember for solving the question for concentric spring. That is load on the outer spring by load on the inner spring, W1 by W2 is equal to D1 square by D2 square. We don't derive this relation, but you have to use this formula in your numericals. Similarly, clearance is equal to d1 by 2 minus d2 by 2 minus d1 by 2 plus d2 by 2. This is the formula for clearance. You don't have to cram it because it's very simple. So this space C is equal to d1 minus 2 minus d2 minus 2. So we are left with this distance. In this distance, we also minus d1 by 2 and d2 by 2. So we are left with C. So here is the formula d1 minus 2 minus d2 d1 by 2 minus d2 by 2 minus d1 by 2 plus d2 by 2. Usually radial clearance between spring is taken as d1 minus d2 by 2. It is also the formula. So net clearance, if you take 2 on the left side, you will left with 2c is equal to d1 minus d2 minus d1 plus d2. So this is your numerical for concentric spring. A concentric spring for aircraft engine valve is to exert a maximum force of 5000 Newton. So this is load given to us, that is load W is equal to 5000 under axial deflection of 40 mm. So deflection is 40 mm. Both springs have same free length, same solid length and are subjected to equal maximum shear stress of 850. So we are given the shear stress for both the springs 1 and 2 is 850. If the spring index for both the spring is 6, spring index C is equal to 6. Find the load shared by each spring, that is W1 and W2. The main dimensions of both springs. Assume G 80 kilonewton per square mm and diametral clearance to be equal to difference between the wire diameters. So this is the question. So let's solve it. First of all, we will calculate the load shared by each spring, that is W1 and W2. So D1 and D2 wire diameter of outer and inner spring, D1 and D2 mean diameter of outer and inner spring. Since diametral clearance is equal to the difference between the wire diameter, it is given to us. So we apply the formula. This diameter clearance 2C is equal to D1 minus D2 minus D1 plus D2. This is diameter clearance is equal to given to us D1 minus D2. Difference between wire diameters of both the springs. Okay, so from here we will get d1 minus d2 is equal to 2d1. Okay, so we know that d1 is equal to cd1 and d2 is equal to cd2. So then we will put the values of d1 here and d2 here, and we will make a ratio d1 by d2 is equal to c by c minus 2. Put the value of c and you will get d1 by d2. Rest of the numerical we will cover in the next part of the video. Thank you guys.